Hello and welcome everyone. In this presentation, we will try to understand the basics behind the working of variable frequency drives. Today, 90% of the motors in manufacturing industries are run using drives. But why is that? It's simple because using drives helps you to have better speed and torque control, and most of all it helps in energy savings, which results in saving operational costs as well. So this presentation is going to be really helpful for people working in industries with variable frequency drives, and also for students who are looking forward to have a better understanding about industrial drives or variable frequency drives. So whatever drives that we see, majorly the manufacturers of drives are ABB, Siemens, or Mitsubishi, or Hitachi. There are a lot of manufacturers, but whatever make the drive be of, the basic principles underlying it are essentially the same. So we'll have a look into that, what all are the basic principles underlying the drives. So let's get started. These are the topics that we are going to cover. So first we'll look into why drives are necessary, and then we'll have a look into the basic operation and the basic components of the drives. Then we'll try to understand the concept of pre-charging. Pre-charging is a very fundamental and important concept on switching on a drive. Next we'll look at IGBT switching and control. Also we'll look at the PWM output of the drive, and then we'll see how inputs and outputs can be interfaced to a drive. Basically inputs and outputs are used to switch on the drive. And then lastly we'll try to understand the need for a braking resistor in case of dynamic braking, and how can chopper be helpful. So talking about the main operation of an AC motor, let's consider a case where we have an AC motor, or let's say it is an induction motor connected to a three-phase main supply. Now this three-phase main supply has a phase difference of 120 degree, as a result of which it gives rise to a rotating magnetic field. Now this rotating magnetic field induces currents in the rotor conductors, and the rotor tries to basically follow the magnetic field. And what is the speed of the magnetic field, rotating magnetic field? It's equal to the synchronous speed, right? And which is equal to 60 into frequency, mains frequency, the frequency of the supply, by number of pole pairs. So if you have a look at this, your frequency is constant, cannot be changed because it's directly connected to supply, and number of pole pairs is same. So you have this constant ns, and your motor will run at only one speed, right? You cannot have a variable speed. Now let's say you have a pump application wherein and you have this motor of rating of let's say 1500 rpm. So in this situation your motor will always run at 1500 rpm, your rated motor speed. Let's say your pump application demands only 800 rpm. So in this case you are wasting rest of the rpm. You will be operating motor at 1500 rpm, but your requirement is can be sufficed at only 800 rpm. And also you are extracting extra energy or power, because your motor will need more power to run at 1500 rpm. So if you are somehow able to run the motor at 800 rpm, this motor will consume less energy, right? And this will result in power savings and operating cost savings as well. So how do you achieve that? Use a drive, variable frequency drive. So what will happen is you can vary the frequency, as a result of which you can vary the synchronous speed, and hence you can operate the motor at 800 rpm. So, and over a time, if you calculate in a very short period of time, you will see that the cost of this drive, extra drive, is overweighed by the savings, energy savings that you have. Alright. So in that way drives are very much useful. If we now further look at the components that comprises a drive, we have a rectifier which converts AC supply into DC supply, and we have the inverter which converts the DC into back into AC supply, which is given to the motor. So basic components that are used to achieve these conversions are: first we have a rectifier. This rectifier can be made up of diodes, or you can have even thyristors. Alright, so this converts AC into DC. And next we have the DC link. We call this as DC link, and we have capacitors here. So what capacitor does is it smoothens out the ripples that are there, and we try to get a more or less DC with the frequency 0. Next we have inverter, which is made up of IGBTs and with freewheeling diodes in parallel. We'll look in further slides the importance of these freewheeling diodes. Basically, it facilitates the continuous current. And then if we look at the waveforms of every stage that we have the input as V line. This is the three-phase input supply to the drive, and the rectifier converts this AC supply into DC. And what the capacitor does is the DC link, it maintains this VDC, the DC supply or the DC link, DC voltage, and also it serves the purpose of smoothing out the ripples of the output. Now this DC output is fed to the inverter, and the gating pulses of these IGBTs are very carefully controlled to produce a PWM output. So this square waveforms that you see here is the PWM output. This is the voltage output of the inverter, which is fed to the motor. So looking in this PWM output, this is the kind of output that the inverter generates. If we carefully look, it is pulse width modulated, which means that the width of the pulses are different. This is very narrow here, and gradually it increases. It reaches somewhat the peak here. This is of the maximum width, and again it reduces, and then same way for the negative half cycle. And if you'll have the look at the current waveform is essentially sinusoidal. Now how do we get this sinusoidal current waveform? We go back. So the motor is an inductive load, right? So if you look at the current waveform here, when this pulse comes, the current gradually rises, and when we have a zero pulse, the current gradually starts decreasing, and again a pulse comes, so this current waveform starts rising again, and then it reduces here. So the width is adjusted such that the current waveform that we have is more or less a sinusoidal waveform, right? So it is because of the inductive load that we have connected that we get a sinusoidal current, but the voltage is pulse width modulated square waveform. Voltage is not sinusoidal. And also the switching frequency of this voltage is approximately around 2 kilohertz. It is configurable, we can have it up to 4 kilohertz also. Next we have a look into the speed and torque characteristics of an induction motor. This is the speed torque characteristics without a drive. So on the x-axis we have the speed, and on the y-axis we have torque. So it starts from here. This is the starting torque which is required to turn the rotor, and this straight line that we see is the load torque. So let's say 100 is the torque required, and the intersection of both these torques is the rated load torque, or this is also called as the operating point. Alright, and this peak that you see is the maximum torque. This is also known as the breakdown or peak torque. So now we try to understand why is this the operating point. Now in this, if you have an induction motor connected to a three-phase supply, you can operate at only one point. You cannot change this point. This is why this is called the operating point. Also, if you see, let's say we try to perturb this point. What I mean is, let's say for some reason we increase the speed, somehow the speed gets increased. So let's say we have come to a point over here where I have kept the pointer. So we see that the speed is increased, but the torque has reduced. So due to the lesser torque, the speed will come back to the operating point again, to the original point. Now let's consider the same scenario in the other direction. Let's say we for some reason the speed is reduced. So as speed reduces, the torque increases. So this increased torque will result in an additional speed. So this will come back to this point. So your motor constantly operates at this point only. Now if you say that why can't it operate here, let's see in this region what happens. If you let's say if you want this to be a operating point, what will happen? If you increase the speed, torque also increases, so the speed will continue increasing. So this cannot be the equilibrium point. Hence this is the equilibrium or the operating point for the motor when you don't have a drive. Next, let us see what happens when we have a drive. So this, you have similar characteristic curve, and you can see there are many curves. Now each curve corresponds to a particular frequency. So what this essentially means that you have a number of operating points at different frequencies. This orange line that you see is the characteristic speed torque characteristics at base frequency. Now if you, this is at 0.8 frequency, this is the torque that you get, speed torque characteristics, and the green lines that you see are respectively at 1.4, 1.6 and 2.0 times the base frequency. We all know that in a motor this V by F is proportional to the flux. Now this flux is also responsible for the torque produced by the motor. So initially when you start the drive at lower speeds, suppose you want to run at a very lower speed, so you have a frequency of 0.4. Now when you want to increase the speed, what do we do? To increase the speed we need to increase the frequency, right? So if we increase the frequency, flux reduces, but we don't want the flux to reduce because we want the maximum torque. So we increase the voltage also in the same proportion, so you get the same flux. So this entire region up to the base frequency you can get maximum torque by changing the frequency and voltage in the same proportion. Now what happens after base frequency? This is 1.0 is the base frequency that you have reached. Now if you increase the frequency beyond this point, alright, so this flux reduces. Now you cannot increase the voltage anymore, because till the time you reach the base frequency you have also reached the base voltage, the rated voltage. So you cannot increase your voltage beyond rated voltage. So to go at further speeds you can only increase the frequency. So when you increase the frequency, this flux reduces, which means the torque reduces. So reduction of flux leads to field weakening. Hence we call this as the field weakening region. And next, the torque gradually reduces following this curve. And if you were to predict how much would be the torque, reduced torque is equal to the, if you say maximum torque is Tm, then reduced torque is equal to Tm into F rated, which is the rated frequency, which is generally 50 Hz in India or 60 Hz in US, by the frequency at which you are operating, the whole square. So hope this is clear. So you can get the maximum torque up to the base frequency, and then beyond that if you increase the speed, the torque gradually reduces. So this is the speed torque characteristics with a drive. Next we have this is the voltage on the y axis and frequency on x axis. Similar to we'll try to analyze what happens as we increase the speed. So as we increase the speed, you need to increase the frequency, and as I was saying in the previous slide, voltage also needs to increase, and this is the point where you reach the maximum voltage, and this is also where you achieve the rated speed of the motor, beyond which you cannot increase the voltage. So let's now overlap this characteristic onto this. Alright, imagine this curve overlapping onto this. So what you have till here, you have the maximum torque, and beyond this you cannot increase the voltage, but you can increase the frequency. So when you increase the frequency, see what happens, the torque reduces, which is the field weakening zone, and gradually torque reduces, follows this line. So ideally this is the dotted line, but this cannot be the case, because initially to start the drive you cannot start with a zero voltage. You need some amount of voltage to develop the torque. So this is why this line is not following the dotted line. So this voltage is sufficient to generate the amount of torque to move the drive, to move the motor initially, and then you increase voltage and frequency in a constant proportion up to the base point. So now we'll have a look into the pre-charging. Initially when you switch on a drive, always pre-charging happens first. Only then is the drive ready to run the motor. It's a very fundamental and a very important concept. So this is the circuit diagram, and this is a resistor, this red box that you see. So why do we need to pre-charge? Now consider the scenario when you don't have this resistor. Alright, so what will happen, this is AC supply and you have capacitor here. So talking about the dynamic characteristics of capacitor at t is equal to 0, just when, and yes, let's assume the capacitor is discharged at t is equal to 0. As soon as you switch on the supply to this capacitor, this acts as a short, and gradually the current rises, and when the capacitor is fully charged, the current flow becomes 0. But initially at t is equal to 0, it acts like a short. So now if there is no resistor in the circuit, this will lead to a very high current, because this acts like as a short, which is undesirable. Hence what we do is, there is a resistor. Initially when for the first time supply is switched on, it is switched on, and this is the path that is taken through the resistor, so that the current is reduced, the surge of current, and gradually the capacitor charges, and when this DC link or the capacitor is charged, a relay is operated and this resistor is bypassed. So here is another circuit diagram of how pre-charging is realized. So this is initially at t is equal to 0, this is the contactor which is picked up. So we have these resistances in series, so that the current is reduced, and once this VDC link is, or the DC or the capacitor is charged, this contactor, main contactor 1 is closed, and this pre-charge contactor is opened. IGBT switching. Now we'll try to understand the switching of the IGBT. Now what we see in red, let's consider this, the IGBT shown in red is switched on. Alright, that means it's conducting. So this is the path, the red line will be the path that the current takes. The return path will be through this IGBT, and this will pass through this coil. Now because the winding acts as an inductor, just when the IGBT gating supply is switched off, or the IGBT is switched off, the current cannot suddenly go into 0, because it's an inductive load. It will have a tendency to keep on the flow of current, which can be fulfilled by a diode. So the flow of current is sustained through these freewheeling diodes. You see the arrows denote the flow of current. Even now the IGBT is switched off, the current flows through the diodes. Next, switching cycle 2. We have this IGBT number 1 fired up along with this IGBT, and current passes through this phase. And similarly, the two freewheeling diodes help in the continuous conduction of current. Now this switching sequence of IGBTs are really very important, and it needs to be controlled very precisely, and it's very time critical. So how do we control the IGBT switching? Yes, basically there is a application specific IC or integrated circuit which sends the signals to these or which sends the control signals or the switching signals to the IGBTs, so that these are fired in a current and appropriate sequence so as to produce a PWM output. So this is the basically a drive also consists of a microprocessor which gives commands, which does the processing, and along with this ASIC, it sends the control signals to the IGBTs. Also these various parameters are stored in the microprocessor, like the rated voltage, rated current, and the maximum speed of the motor, and based on those calculations the firing angles are calculated and firing is controlled. So just to show how important the switching sequence is, let's consider a case where these two IGBTs are fired up by mistake. What will happen? It's a short. So this is how critical the switching is. Inputs and outputs. So when we say a drive also has an input output interface which consists of digital IOs, analog IOs, or serial communications also. Now this IO interface is provided so that the motor can be switched on and off by a push button, or through a controller the command can be given to the motor to run. Also the speed can be sent, the set point can be set by an analog input output. So this is the IO interface, which again sends the signals to the microprocessor, and this controls the drive. This is basically how a drive is controlled. When you have a push button, you send through the push button on command through this IO interface to the microprocessor, and this processes your on command and starts firing the signals. And based on the speed that you have set, the firing pulses or the firing angles are of these IGBTs are controlled in such a way so as to control the speed of the motor by varying the voltage or frequency. Braking chopper and resistor. This is basically required when we have regenerated power from the motor. So when you have to stop the motor, or whenever you have power which is regenerated from the motor, it is fed back to this DC link. So we have a resistor in between to absorb this power. But what if the power which is regenerated is really high? So for such cases we have a chopper in between. Chopper is nothing but you can say an IGBT whose firing is controlled so that the power is dissipated out in the braking resistor in a controlled way. So basically when a motor is regenerating, the flywheeling diodes conduct and rectify the generated voltage from the motor. These diodes basically will convert this power back from motor. This will convert it into a DC supply, and this DC supply continues to charge the DC link capacitor. When the DC link voltage reaches a preset limit, the braking IGBT or this IGBT is energized, which allows the DC link capacitors to discharge through this braking resistor. Now when the DC link capacitor charge falls below a minimum level or some set level, this IGBT is switched off, which allows the capacitor to recharge. So this is the function of what we call as a chopper, braking chopper. Hope the presentation was really helpful. If you have any questions regarding drives related to this presentation or any other concepts, please do post it in your comments. and please do like and subscribe our channel, because we'll be posting many such videos similar, which will be really helpful for clearing your basic fundamentals. Thank you.